Hello everyone. So this is the third part of elimination reaction. So here our focus will be on E2 mechanism, different factors related to it. Okay. So E2 elimination, unlike E1, it is bimolecular, which is clear from the rate expression. You can see it is rate constant, that is K, into the concentration of alkyl halide as well as the concentration of base also. In case of E1, you have seen it is only the concentration of alkyl halide, not base. But here both of them are present, so that is why it is bimolecular. The rate of the reaction is second order. So one with respect to alkyl halide and base one with respect to base. So total it is second order. So dependent both on the concentration of substrate as well as base. Now unlike E1, this is a single step reaction. Here both the proton removal and the leaving group both will be removed simultaneously. So that is why it is single step concerted process. Sometimes stereochemistry of the starting material is important. Now what is the details about it, that I am not going to discuss it here. There will be separate video where stereochemistry related to both E1 and E2 I will discuss and also compare. So there we will see what is the case. That is why the stereochemistry of starting material is important. So let's take this general example. Here you can see this is the carbon hydrogen bond. This hydrogen, it is to be attacked first by the base. I should not say first because both the processes are going on simultaneously. So the cleavage of this C-Br bond, which is our leaving group, and the cleavage of this CH bond, both are going on simultaneously. So we are calling this carbon as alpha, we are calling this as beta. Fine. So this is our product. So basically it is removal of BH and also Br minus. So from one substrate you are getting total 3 species. Okay, in elimination it is always, you will see after reaction the number of species that is increasing. So both the bond breaking of CH and the bond breaking of CBr both are going on simultaneously. Now we will take a particular example. So 2-bromo-2-methyl propane, that is our molecule, our starting material. We are using the base hydroxy. We are getting 2-methyl propene. So all these hydrogens are actually beta hydrogens. All are equivalent, so any of them can be removed. So hydroxide, we are calling it base. It is not very good nucleophile, and obviously in elimination we use the term base mostly, not nucleophile. Hydroxide cannot act as nucleophile in this reaction because of the bulky tertiary halide. Okay, so it cannot act as good nucleophile. And also HO minus, if you compare nucleophilicity and basicity, it is more basic. So that is why we are getting elimination product. So here hydroxide is acting as a base, so that is why it is abstracting proton. It is not acting as nucleophile. Next we will see the transition state regarding this reaction. So as I have said that this is single step. So obviously there is no intermediate. This is our transition state. You can see there are total 4 dotted lines. Fine. So the bond formation between this hydrogen and oxygen, the bond breaking of C and H, the new bond between C and C, these two carbon, and the bond breaking between this carbon and bromine, all are going on simultaneously. Fine. So this is a transition state. There is just one activation energy. So any factor that will increase, as there is a single step, so you can also call it RDS step. In E1 we have seen that the first step, that is the carbocation formation step, is the RDS step, but here it is a single step, it is the RDS step, you can call it. And our final product is Me2C double bond CH2, that is 2-methyl propene. Okay. Now what is the evidence that support the E2 mechanism? So first of all, it follows second order kinetics, which is experimentally observed. The second thing is kinetic isotope effect around 3 to 8. The value may be ranging from 3 to 8 that is observed. So it proves that the cleavage of CH bond and if you take the deuterated version, just think about the previous molecule, that is Me3CBr. If you have taken the corresponding deuterated version, that is CD3, CD whole 3, CBr. Please excuse me for my handwriting. So CD3 whole 3 CBr, if we have taken this molecule, that is the deuterated version of the previous molecule. Just think about this molecule, 2-bromo-2-methyl propane. If you have taken deuterated version, so CD3 whole 3 CBr. So if you have taken that molecule and if you are doing the same reaction under same condition, then we have seen that the KH by KD value, that is 3 to 8. So KH by KD value means the reaction when you are using the normal Me3CBr and when you are using the corresponding deuterated version of the same molecule, this value, it may range from 3 to 8. So that means that this carbon and hydrogen, this bond cleavage that is taking place in this step. So both the bond breaking, that is the CH bond breaking and the C leaving group bond breaking, both are going on simultaneously. So this strongly supports the cleavage in RDS step, or you can say in the single concerted step. Fine. The next proof is there is no rearrangement. So it further proves that there is no formation of carbocation intermediate. Number 4, most T2 reactions are stereospecific, indicating particular relationship between the departing groups, and it is a concerted process. So stereospecific means suppose there is a possibility of 2 products, but among them only one we are getting exclusively. So in that case we call these type of reactions as stereospecific. So it means there is a particular relationship that is required, that is why we are getting only that product stereospecifically. There may be suppose another arrangement of departing group, that is also possible, but maybe that is energetically not so suitable. So that is why that product we are not getting. And the last point is 2-step mechanism will be ruled out if you do the reaction with deuterium leveling. So what is that? Let's look at it. So suppose your starting material is this. This is again a general structure. Now when you are using ethoxide ion in presence of deuterated ethanol, that is ETOD. So one arrow is downward, that is the E2 mechanism. If it is taking place, then you will get this molecule. Fine. But suppose you are doing, this is also suppose in presence of ETO minus and ETOH, that is not the deuterated version you are using, then you are getting this molecule. But if you are using ETO minus and ETOD, then there is a chance that this type of carboanion will be formed. So if this carboanion is formed, then obviously this deuterium, it will, that is this negative charge, it will take this D from here, and finally there will be CD bond formation. So basically if you are doing the reaction in presence of these reagents, and if you are not allowing the reaction to complete fully, because if you are allowing the reaction to complete fully, maybe again you will get alkene. But that we do not want. We just want to see if we interrupt the reaction in the middle, then is there anything else we are getting? So we have done the same thing, that is we have interrupted the reaction in the middle point. We have not allowed the reaction to complete fully. In that case, you are getting this type of molecule. Experimentally that is observed. So it proves the formation of this type of carbanion intermediate. Okay, but actually we are not getting it. So it again proves that this type of carbanion, it is not formed at all in the reaction medium. Okay, theoretically you should get it if it is going through carbanion intermediate, but actually you are not getting. So that means carbanion mechanism is ruled out. That is 2-step mechanism is ruled out by the following experiment of deuterium leveling. Okay. Stereoelectronic requirement in E2 reaction. Yes, there is some stereoelectronic requirement. So here you can see in the picture, some Newman projection is drawn, and we are mainly focusing on hydrogen and X. That is the main 2 group that are going to removed. Fine, HX. removal of HX. That is the main point of main eliminated group. So in the first Newman, both HX, they are on the same plane. In the second Newman also, they are on the same plane. But what is the difference? Here the degree between them is 0 degree. But here the degree is 180 degree. That is the difference. So the first arrangement, we are calling it that the substituents are in syn periplanar arrangement. You can also call it eclipsed. In the second one, they are in anti-periplanar arrangement or staggered arrangement. Now, the alkene is formed by the overlap of CH sigma bond, that is this CH sigma bond, and the CX sigma star anti-bonding orbital, that is this is the CX. So sigma star of CX and sigma of CH. So the alkene is formed by the overlap of this sigma bond from CH and sigma star from CX. These two orbitals must lie in the same plane for base overlap. Now you can say that in syn periplanar they are also overlapping, in anti-periplanar also they are also overlapping. Yes, that is true, but still anti-periplanar it is more preferred compared to the syn periplanar. Why anti-elimination is preferred? Because in anti-elimination you can avoid the repulsion that is generating from the electron rich base. Suppose your base is attacking here, suppose, okay, and X is removed in the form of X minus. So both are electron rich species, so there may be some repulsion between the two negatively charged species. One is X minus, that is removed, because that will also be removed, that is, this bond will start breaking in the transition state. Fine. So there may be some repulsion between these two electron rich species. So that is one problem if the attack is taking place from the same side. That is, if H and X, their degree, they are in the same plane and the difference of degree is 0 degree. So that is one problem. And the second problem is steric hindrance problem, if the base is attacking from the same side. But if it is backside attack in the second case, then you can avoid these two problems. Fine. And backside attack is allowed only in anti-periplanar geometry. So that is the reason anti-elimination is favored over syn elimination. So this is the first box, the picture that you are seeing, that is the Newman projection. In the second case, that is another view, that is actually Sawhorse projection, where it is more clear that how the base, when it is attacking from the back side, then how we can avoid these two problems. One is steric hindrance problem, another one is repulsion between two electron rich species. One is base, another one is departing X minus. Okay. Now what is the proof of this stereoelectronic requirement? So here we will discuss a problem, and through this problem you will be able to understand it. So what is the problem? Erythro 1-bromo 1,2-diphenyl propane, this molecule, see this is actually alkane and there is a bromo, halide is present. It undergoes base induced dehydrobromination. Dehydrobromination is removal of hydrogen and Br. Only by anti-pathway to give cis 1,2-diphenyl propene, that is our alkene, the final eliminated product, exclusively. So you are not getting the trans. So you can call it that though there is possibility of trans and cis, but you are getting only cis. That means it is showing stereospecificity. Okay. Now this is the molecule, general structure of a molecule in Fischer projection. And for Fischer projection, how you can convert it to Sawhorse? See this B and C, how it is placed here, X, Y, Z. So A and Y both are downward. Okay. Now the same molecule, this portion is completely intact, but if you rotate this carbon, you can get this structure. So all these structures are equivalent. So why I am showing you this in general form? Because now I will draw the actual molecule in Fischer form, Fischer projection first, and then I will change it to Sawhorse. That is why first I am showing you the general way how we convert from Fischer to Sawhorse. So this is the Fischer projection of the molecule that is mentioned in the question. That is erythro 1-bromo 1,2-diphenyl propane. So now we will see how we can convert it to sawhorse. So when we are converting it to sawhorse, two arrangement you can do. See, in the first case, if you look at this portion, it is same for both the arrangement, right? But only this carbon, the arrangement is different. So in the first arrangement, you can see bromine and hydrogen, they are in anti arrangement, but in the second case it is syn. So when it is syn, bromine and hydrogen when removed, look at the position of the two pH group, they are on the opposite side, so final product it is trans. But from the anti arrangement, what you are getting cis product, right? So basically here from the anti arrangement we are getting cis 1,2-diphenyl, but from the syn arrangement we are getting trans 1,2-diphenyl. So exclusively as we are getting the cis product, that is we are getting exclusively this product, not this one. So it again proves that why anti arrangement is preferred over syn arrangement, right? So that is all for this video. This is not just the end of this E2 mechanism. I will come to you with some more information regarding E2 mechanism. In the next video we will see that in some cases syn elimination may happen, special cases, then consecutive E2 elimination and E2 elimination in cyclic compounds. All those things we will see in the next video. Okay, so until then, goodbye, and if you find this video helpful, please like, share and subscribe. Thank you for your time.